Welcome everyone. Today's lesson is entitled Finding Models for Sinusoidal Graphs in Data Day 2. This lesson should represent a follow-up to the previous lesson dealing with sinusoidal models, so we'll do a little bit of a review and then expand it as well. So you will need a graphing calculator, by the way, for this lesson, so grab your graphing calculator, and if you can ensure that you are in radian mode on the graphing calculator, that'll make everything transition smoothly along the way here. All right, so let's start with example 1, just a nice little application review problem, and then we'll take it from there. So just a Ferris wheel problem. We've looked at this before. In fact, we've investigated this pretty thoroughly, that when we graph a function for the height in terms of time on the wheel, we get a pattern on the coordinate plane that is sinusoidal in nature. So I guess what I'd ask you to do just right off the bat is just give me a little L-shaped first quadrant coordinate plane, and we're relating two variable quantities, so t and the height in terms of time, so h of t. And let's see what we've got going on. Getting on at the platform, which is 8 feet above ground, which will be our lowest point. So we don't need a whole lot here in terms of the scale. We just need the low point, which is 8. The Ferris wheel diameter of 44 feet. So this is where we do want to be a touch careful. So we're getting on, the bottom of the wheel is 8 feet above ground, and then the top of the wheel would be that 8 plus the 44. So that's where you're just going to be a touch careful here. So it looks like we're going to fluctuate from 8 feet above ground to 52 feet above ground based on the 44-foot diameter there. And it looks like our period, one revolution, would take 27 seconds, and that's looking pretty good in terms of all we need with the numbers. And now we've seen this before, so I don't want to overplay it too much here, but should be a nice little sinusoidal curve, one cycle of it, and obviously we're starting at the lowest point, and after 27 seconds, we end at that lowest point. All right, so graph a function for their height in terms of time on the Ferris wheel. Looks like we've done that. And now what we're going to do is part B, which is writing the sinusoidal function to model the graph. And a couple things to keep in mind, and this is where I want to overlap it from the previous lesson. If you're wondering, all right, well, how am I going to find the midline and then the amplitude? You know, we found a couple of nice ways to do that. So I always like to do midline first. And if you remember, the midline is the maximum and the minimum added together, and then divide by 2. Essentially, it's the midpoint of those two values. And so I do that. 52 and 8 make 60, divide by 2. So the midline, essentially, the d value would be 30. That's great. And again, just in terms of finding the amplitude, rather than trying to count things out, or I don't know, some other ways maybe to pull that off, but we figured out that the amplitude would be the maximum minus the minimum divided by 2. It's sort of half the distance between the maximum and the minimum. Hang on one sec. Let me just change that. There we go. So 52 minus 8, and then divide by 2. And when we do that, of course, we get 52 minus 8, which is 44, and that's a 2 on the bottom there. And so what do we got? 44 divided by 2, 22. All right, great. So let's put those into the mix, or at least the midline. So there's the y equals 30. I'll just throw a 30 right there. And you can kind of see how far is it from this midline up to the top. It's 22 units from 30 up to 52, or it's 22 units down from the 30 to the 8. So the amplitude is 22 here. All right, well, let's put a couple things together. We've got our period, we've got our midline, we've got our amplitude. And by the way, I'm going to just throw that in the mix here while I'm thinking about it. Period is 27 units, and in this case, the units represent the number of seconds. So we've got that, and we're ready to go. All right, the only thing I would say is when we do write a sinusoidal function to model the graph, the first thing we want to at least decide is, do we want to use sine? Do we want to use cosine? Do we want to use a negative in front of the cosine? Those were the three scenarios that we've looked at thus far. And so I'm seeing that the y-intercept is at the minimum of the cycle. And so as a result, because the y-intercept is at the minimum, and I'm going to actually write that here, so y-intercept is minimum, and so as a result, we called it like a flipped cosine or a negative cosine, whatever you want to do. Sort of means the same thing. Essentially, we're going to throw a negative out in front of our cosine function. So if you want to write flipped cosine here, that's fine, or negative cosine, either way works. Again, because normal cosine would start at the maximum of the cycle. Normal cosine would look like that, if you can see my pen there. In this case, to get that to match this, we have to flip it. All right, so let's go ahead and write it. Y equals, we're going to do a negative in front of our amplitude, so negative 22 cosine. Now here's where we do want to be careful. Please do not forget this. We do not want to put a 27 there. Remember the b value, that's the number in front of the variable. That b value is going to be 2 pi over the period, so 2 pi over 27. And in fact, I'm going to be a little more variable specific on this, sorry. Just feel a little better about that. So instead of y equals, let's go with our function notation. So height in terms of time, so h of t equals. And now we've got the height in terms of our independent variable, which will be t. I like that a little better. And then certainly plus the midline on the back, and we're good to go. All right, so just a little review problem to get us thinking, and remember just the calculations to get midline and amplitude if it's a little harder to just kind of count some things out. All right, let's move on to the next piece. So we've seen a little bit about this, but let's kind of go through the nature of what it means to be sinusoidal. So sinusoidal, of course, it represents quantities that are cyclical in nature, meaning the cycle repeats again and again and again. And it also means that we have a natural maximum and a natural minimum. And the values fluctuate cyclically in between the maximum and minimum. So there are a variety of natural phenomena that occur where they are cyclical in nature and they fluctuate between a maximum and minimum. So this just happens to represent one. If you're looking at example 2, it looks like I've got sunrise times in Boulder. So right here, so sunrise times would represent one of those natural phenomena that fluctuate, and there's a maximum and a minimum, and it's cyclical in nature. So I guess I got this online, got 5 data points. Kind of needed 5 to get the full cycle here, so that's why I went into the next year. So even though day 80 and day 445 produced the same sunrise time, I needed this last data point to create a sinusoidal function on the calculator. So that's exactly what we are going to do. So this is where you will need your graphing calculator handy. And so we have just 5 points. And I'm going to bring up my calculator, and to create a regression, so to have the calculator come up with a best fit model for the data, we're going to do it kind of in 3 steps here. We're going to enter the data in, then we're going to view the data, and then we're going to ask the calculator to model the data based on the information we have. So if you would, go ahead and hit Stat for me, and then Edit. And if you have anything in your L1 or L2, just clear. So you would go up to L1, hit clear, and then enter. And then go up to L2 and hit clear, and then enter. And now let's go ahead and enter our data in. So sunrise times represent the dependent variable. Those will go in L2, by the way. The day of the year would represent the independent variable, and so those will go into L1. So I've got 80, so the 80th day of the year, and then 172. Oh, let's get that a little better there, 172. There we go. And you guys are sure quicker than I am with this stuff. And lastly, 445. So I have my 5 x values, essentially. Now we need to match up the 5 y values. Now just a couple things here. These two are during daylight savings times, and so I had to kind of put them back in the standard form, or standard time, to make sure that everything is completely uniform there. So they're all in standard time as a result. So officially, on the summer solstice, the actual sunrise time is 5:32, but if we put it back in standard time, that would be 4:32. So just wanted you to be aware of that piece. All right, anyway, so I've got these values right here, 6.017, and just go right down the line if you would. Okay, getting closer. And lastly, this one. All right, so 5 x values matching up with 5 y values. And what I'm going to have you do is go ahead and hit the y equals. And if you haven't already, I'm going to go ahead and put my plot 1 on. So I'm going to highlight that piece. And I'm going to hit zoom and number 9. And you see we have our 5 points here. And kind of get that cyclical idea where there's a little bit of a midline, max, and min situation going on. And so what we're going to do is try to get a sinusoidal regression to model this. So when you are ready, if you would, go ahead and hit Stat for me, please. And we're going to move it over to Calc. And we've worked on a variety of regressions before in this class, and you've done some in your other classes too. But you can see them all as you start working down the list here, all the different types of regressions that you can create. And if you go down, you should see one that says SineReg. And so I'm going to go ahead and get that going. Now I have a TI-83, so it brings me to this screen right here. If you have a TI-84, your screen's going to look a little different. I'm going to tell you what to do in just a second. So what we want to do at this stage is I want the calculator to plug the regression into the y equals. So for those that have a TI-84, what I want you to do is scroll down. You should see a little further down something that says Store Reg EQ, store the regression equation. So if you would, just scroll down there. And now that you're scrolled down there, if you could hit the vars button for me. So I'm going to hit vars. And then move it over to the y-vars. And then hit number 1 for function. So I'm going to enter it on that. And we could put it in anywhere. I'm just going to put it into the y1. So I'm going to hit enter one more time. So notice y1 pops up here. Again, if you have the TI-84, where it says store reg X, essentially, store regression equation, you're going to put it there. Now, if you have the TI-84, just go down to calculate and hit enter. For me, I just hit enter right here, and it's going to think for a moment, and it comes up with our sinusoidal model. Now, just one thing to note, it uses sine as a default as opposed to cosine. Here's your A, your B, your C, and your D, which are all given numerically here. The calculator uses plus C where we've been using minus C, but it really doesn't matter. We'll just do plus and whatever this C value is right here. All right, so let's write the model. And so I have y equals, and I've got 1.380 sine 0.017x plus 1.663. Let's get that better. There we go. Close it on off. Plus 5.888. All right, so this models the sunrise time in Boulder given any day of the year. So this day of the year is the X, sunrise time is Y. Now one thing on the calculator quickly, I'm just going to show you. If you'd hit graph for me, please, that would be great. And notice, it might not be perfectly sinusoidal, but it's pretty close there. We get a nice sinusoidal curve fitting through our 5 data points right there. That's great. Okay, now this might differ from both our perspectives. I'm doing this on March 30th. Now you're going to, ideally, you would do it on the day that you're watching this lesson. So March 30th for me happens to be day 89 of the year. And so what I'm going to do is predict the sunrise time today for March 30th, so day 89, which means I'm going to put 89 in for X. If you can take a moment and see what day of the year it is for you, that would be great. You put it in for X, and let's go ahead and see what happens. So I'm going to go ahead and quit this for the moment. I'm in radian mode on the calculator for all these models, radian mode, and I'm going to type in 1.38, I'll throw the 0 in there just for kicks, sine 0.017 times 89, so my X value is the 89, plus 1.663, close it on off, plus 5.888, and I get about 5.84. Okay, so let's see what we have here. So from the model, we get 5.84. Now this would be, remember, we just have to be a touch careful here. This is standard time because everything in the model is put in standard time, but because it's March 30th, it actually happens to be after daylight savings. So as a result, 0.84, if I do 0.84 and divide by 60, I get 50 minutes to the hour. And so in reality, this would be 6:50 a.m. So instead of 5:50, because of this 5 right here, I have to spring it forward because daylight savings. So it's 6. And then if I take this number, the 0.84, and multiply it by 60, that would give me 50 minutes out of 60. So 6:50 in the morning. All right. Now, it just so happens, I looked it up before teaching this lesson, and the actual is, it was 6:48. So you could see how really incredibly close the model is. So is it perfectly sinusoidal? No, maybe not. But based on just even 5 data points, obviously if we had more data points, probably could have even gotten more accurate with it. But even with just 5 data points, you see how close the model predicted the actual. All right, I would love to see, if you can do it, look yours up as well, see how close your model is compared to the actual. All right, very good. Let's go on to the next piece. So let's add one more component to sinusoidal models, the phase shift. So if you remember the day 1, we wrote our models trying not to use a phase shift. So remember, if it started at a maximum, we'd use cosine. If it started at a midline, we would use sine. If it started at a minimum, we would use cosine with a negative out in front. What happens when it doesn't start at one of those 3 points? Well, we need a phase shift. And we'll start to take a look at that piece coming up. All right, well, how do we determine the phase shift of a sinusoidal function? We've already looked at this. Phase shift, of course, equals C over B, the way we've been writing our functions. So C over B, so in this particular case, remember the B value is the number in front of the X. So phase shift here would be the C value, so pi over 4 over 1, and so that's obviously pi over 4. Now remember, positive phase shift means that the function is moving to the right on the coordinate plane. Please do remember that. So when I have a positive phase shift, that means that it's a shift to the right. In this particular case, because remember it's bx minus c, that's our default inside the parentheses, this really to me reads 2x minus negative pi over 4. So the c value here is actually negative pi over 4. And as a result, when I do negative pi over 4 divided by 2, and anytime I get that little quick compound fraction, remember outside over inside. I've shown you that before. So think of it as negative pi times 1, so negative pi, 4 times 2, so negative pi over 8. Excellent. So remember, a negative phase shift means that we're moving to the left on the coordinate plane. Keep that in mind if you would. All right, let's move on. So, I like this one a lot. It's time to start thinking a little bit more outside the box with these. So sine and cosine functions produce the same graphical pattern on the coordinate plane. One is simply a phase shift of the other. Use that idea for the next example. So sine and cosine, they look the same, right? That nice sinusoidal curve up and down forever and ever and ever. So rather than just writing one function to match this graph, I want us to see if we can write several functions to match this graph. So, first order of business. A couple of the tick marks didn't really come through here nicely, so can you put a tick mark right there? And that tick mark happens to be pi over 2. This one happens to be pi. There's 3 pi over 2. And this one right here got a little covered up. That's 2 pi. So I kept it relatively simple. So again, pi over 2, pi, 3 pi over 2, and 2 pi. Awesome. So the period happens to be 2 pi. Period is from here to here. Very nice. Midline is y equals 0. Amplitude is 3. All right. Now, if I asked you to just write a function here, you would absolutely, positively choose sine because it starts at the midline and we're going up. Fantastic. So you'd be like, all right, I'm going to use sine. And because I can use sine here, I won't need a phase shift because this is a natural sine function because it has a y-intercept at the midline, and so it's a natural sine function. So you would write y equals 3 sine of x. Remember the b value, the number in front of the x, is just 2 pi over the period. So 2 pi over 2 pi is just 1. All right, perfect. Hey, that was 1. Now I want a bunch of others. What if we tried to write a cosine graph for this? So I would start and be like, all right, well, great, the amplitude's 3, and I'll do that, and cosine. Okay, but cosine doesn't look like this. Cosine has a y-intercept at the top. So go ahead and just do a little bit of a maximum up here, kind of what cosine would look like. That's normal cosine, right? Starting at the maximum. I need to get cosine to fit this graph. Well, I can actually do it a couple different ways right off the bat here. Do you see that I can take this right here and move it pi over 2? So 1 tick mark, I'll move it pi over 2 to the right. And so as a result, if I just shift this pi over 2 to the right, I could now get normal cosine to fit this graph right here. Well, if I want to go pi over 2 to the right, that's a positive phase shift, so it's x minus pi over 2. So do you see how, in reality, each of those should match? So I'm going to go ahead and go to my y equals and clear that out. And I'm going to hit 3 sine of x, and I'm going to hit zoom and number 7. And if you could do that as well, that would be great. And notice what we get there. Does it look like it matches this graph? Absolutely. So that was 1. Now if I want to do another, let's clear that out, and let's try 3. And then instead of sine, let's do cosine of x minus pi over 2. And notice that the graph is the exact same because I took normal cosine and I moved it pi over 2 to the right. All right, cool. Let's do another one. In fact, let's do another cosine. All right, how about this one? So here's cosine right here. I moved it pi over 2 to the right, didn't I? Well, if you notice, couldn't I have probably moved it over here? And so if I move it this way, by the way, there's negative pi over 2. There's negative pi. There's negative 3 pi over 2. Do you see if I shifted this, normal cosine, and if I went 3 pi over 2 to the left, I could get it perfectly now to fit that graph right there. So instead of shifting it right pi over 2, I could have gone left 3 pi over 2. And that would work. I'm going to let you graph that one. Grab your calculator, put that in, but it should give us this exact same graph. How about this one? Been talking about this one a lot. How about a negative cosine? So we've done sine, we've done a couple cosines. Let's do negative cosine. Well, what does negative cosine normally look like? Well, negative cosine normally looks like a minimum right on the y-axis there. All right, so how do I get a normal flipped cosine to match this graph? Well, it looks like one way I could do it is just move it pi over 2 to the left. So if I take this and just go pi over 2 units to the left, now I've got it. And so how do I move pi over 2 units to the left? Well, in this particular case, you would just be x plus pi over 2 there. Now, this is a little easier because my b value is 1. When the b value is not 1, it does get a touch harder. But you can kind of see how nice that is. And I could keep going again and again and again with these. I'm just going to do that fourth one, negative 3 cosine, and then x plus pi divided by 2, hit graph, and hopefully we've got a winner. There you go. Looks pretty cool. All right. So I just want you to be aware of the fact that, yeah, obviously if I just said write one function for this graph, you would go this way, right? And you wouldn't have to use a phase shift. But as I said, sine and cosine functions are interchangeable because they make the same pattern. So just shifting one to fit the graph, you can make as many of these functions as you want. Again, theoretically, there are an infinite number of options here. All right, guys, let's get into the last piece. Well, let me just read the blurb, and then we'll do the last example of the day. So up until now, we've only looked at writing functions for graphs with a y-intercept at either the maximum, the midline, or minimum. That way we could avoid having to use a phase shift. The next step is to write a sinusoidal function for a graph with a y-intercept that is not one of those 3 points. And by the way, there are a couple different ways to do this. So I'm going to teach you one way, but as it says on your paper, if you'd like to explore an alternative way, please don't hesitate to ask and I'll walk you through. So the way I'm going to do it is actually a very formal way. Works beautifully. So I'm just going to go with that, but as I said, there are always different ways to perceive things, so if you see or are interested in seeing a different way, by all means. All right, let's go through it. So first and foremost, do you notice that y-intercept, which is right here? That's always the one I look at first. Do you notice it's not at the minimum, it's not at the midline, and it's not at the maximum, so we can't just do what we've been doing and avoid a phase shift. We need a phase shift. So let's go for it. So first things first, it says determine the d value, and the d value is going to come from our midline. I'm seeing it right here. My perception's not great, but I'm seeing that middle is right there, right in between the maximum of 5 and the minimum of -1. And again, if I forgot how to do that, that would be 5 plus -1 divided by 2, and it looks like 2. All right, d value is 2. The a value, so that would be, really coming up with the amplitude here. So that would be 5 minus -1 and divide by 2. So 5 minus -1 is 6, divide by 2, and that gives us 3. And you can see right here, if I just count from here to the top, that's 3, or from there to the bottom, that's 3. All right, now the b value will come from the period. So I like seeing the period from the y-axis if I can. So how long does it take to get to that exact same spot going in the exact same direction? So from here to here is not the period because this is declining, whereas that's inclining. So that's not the period, everybody. I'm thinking the period is right here in terms of the repeat. So from there to there is the period. 2 tick marks on this coordinate plane, and it says each horizontal tick mark is pi over 2. So that would be 1 pi over 2, 2 pi over 2. So the period is pi, and so you might want to just jot that down somewhere. Period equals pi, but the b value is always 2 pi over the period. Just make sure you do remember that. So the b value is 2. All right, very good. So we have A and B and D ready to go. We cannot avoid the C value here. Because the y-intercept is not at one of those 3 main points, minimum, midline, or max, then we need to incorporate some type of C value. So it says for part D here, use the model, and by the way, I'm just defaulting on sine, kind of like what your calculator did, but you can do cosine with this, you can do negative cosine, you can do anything, it doesn't matter. Again, infinite number of ways to write these functions. But in my case, I'm just going to go with sine, that's all. So it says substitute A, B, and D into the function. In addition, here's the key. Notice the one thing I had to give you. I had to give you an x and a y. So remember how functions work and graphs work. If it is a point on the graph of the function, then it has to make the equation true. And so we're going to use the x and the y in order to find the only thing that'll be missing, which will be c. All right, I'm going to get right into it. So y equals, so the y value is 5. And let's see, I get A is 3, sine, B is 2, the x value that matched the y value is 5 pi over 8, minus c, which is unknown, plus 2. All right, very good. Now we're just going to solve for c. So everybody, if you would, from the outside in, subtract 2. So I get 3 equals 3 sine, and I'm going to put these together, by the way. It looks like 2 times 5 pi, that would be 10 pi over 8. 10 pi over 8 reduces to 5 pi over 4 minus c. I like that. Everybody, if you would, divide by 3, and I'm sorry, I'm going to have to come over here. So I've got, when I divide by 3, I get 1 equals sine 5 pi over 4 minus c. Again, just working from the outside in. Everybody, if you would, how do we get rid of sine? Well, we need to use the inverse of sine to get rid of it. So we're going to inverse sine on 1. Quit. Second, everybody. Inverse sine, 1. And by the way, that number happens to be exactly pi over 2, but for our purposes, the decimal is going to be just fine. So about 1.57 equals 5 pi over 4 minus c. All right, so let's see. I'm going to bring the c on over and make it positive, and then I'm going to subtract this. So c equals 5 pi over 4 minus 1.57, and I get, as a result, c equals, as a decimal, 2.357. Now, you do not need to know this at all, but it just so happens that 2.357 is really the decimal approximation of 3 pi over 4. Just FYI. But you can absolutely positively just go with that right there. Not a big deal. So guys, we've got it. I needed a c value for this, and so I used A, B, D, and the point in order to find c. Now we take a step back and we write our model. So 3 sine 2x. Now again, if you want to put the decimal there, that's totally fine. I'm going to put it as minus 3 pi over 4 and then plus 2. All right, let me grab the calculator and we'll wrap this on up here. So I grab the calculator and I'm going to type it in 3 sine 2x and minus 3 pi divided by 4 and plus 2 on the back. You can just watch me do this. I'm going to change my window a little bit here just to accommodate the maximum. But let's hope for the best. Let's see what we got. And so what do you think? Does that seem to match it? One way that we can quickly tell, if I go to second and trace and go to value, and I actually type in an x value of 5 pi over 8, it should, notice, give me a y value of 5. And that's it, 5 pi over 8, comma 5. So this graph matches the graph right here. All right, guys. Again, a couple ways we could have done this as well. I taught you a very formal way. Try that out. Use this as a reference to help you with any of the practice or whatever problems that you come across there. But it works out pretty nicely, doesn't it? All right, guys. Thanks so much. Appreciate it. Please do let me know if you have any questions.